Hi students, welcome to AM Teachers Tech. So today's topic is we are doing digital signal processing, module 1, lecture 1. Under that the first topic is frequency domain sampling and reconstruction of discrete time signal. So this is your fifth sem core subject, that is your digital signal processing. Okay, ECE branch. So the first is when it comes to digital signal processing. So what is signal here? So signal could be defined as a function that conveys information. So it is something called as, here you can call it as a function which conveys some information. Now in this function you have a single variable. It could be single variable. If it is a single variable, then we are calling it as one dimensional signal. If it is dependent on one variable, then a single variable, then we are calling it as one dimension. Now if this signal is dependent on two or more variables, then we are calling it as multi-dimensional. Example for the single variable is your speech signal, and example for your multi-dimensional is your image signal. Now in signal, again you have two types. One is your analog signal and second type of signal is your digital signal. Now if you see here, the subject is digital signal processing. So that means we are processing the digital signal. It's not analog signal, but the natural occurred signal is your analog signal only. We take an analog signal here. See, the axis of this signal is represented as t. So this x-axis is represented t. So the signal, we are representing this signal as x of t. Okay, so this is your analog signal. Even you can call it as continuous time signal. Now the same signal, if I draw here, now if you see this signal, now the axis of the signal is represented as n. So the signal, I'm going to represent it as x of n. Now this signal, this is also an analog signal. So what I can do, if I take a samples at a specific instance of time like this, if I take a samples at specific interval of time with equidistance. Now this distance should be equal. So this distance, equal distance, I'm going to represent it as omega w. Now this signal, once this process is called as sampling. Once if I do the sampling of analog signal, we are calling it as a discrete time signal. It is not digital signal. For the digital signal you have a two more process. You have to do quantization and then you have to do encoding. Then the resultant data will be in terms of bits, binary bits. Then that signal we are calling it as a digital signal. Okay, so if I take a sample of analog signal at equidistance, then that signal, resultant signal, I'm going to call it as DTS. That is discrete, what is a discrete time signal. Okay, now if you see this omega, we are going to represent it as 2 pi by n. Why we are representing as 2 pi by n means, so what is this? This period we are taking as 2 to, the period between this one we are taking as 0 to 2 pi. And we are samples we are taking for the number of samples we are taking as n samples. So what is this? Omega is equal to 2 pi by n into k. So k will define what is the value of this. Now if k is equal to 0, then what will be omega value? Omega value will be also 0. So that is this sample. It is representing this sample. Okay, if k is equal to 1, then what will happen? So the omega will be equal to 2 pi by n. Okay, that means it is representing this sample. Same way I can take it, k is equal to 1, k is equal to 2. So what is sampling? Sampling, it takes one of the finite value of analog signal, signal at specific instance of time. That is, this distance will be equidistant. Discrete signal, how I am representing? We are representing as x of n. Now this x of n, we are taking Fourier transform here. If we take a Fourier transform of this signal, so the resultant signal will be in frequency domain, and that one we are representing as x of k, or we can even represent it as x of omega. So now x of n is your discrete time signal. Okay, so this is in time domain. If we take Fourier transform of this signal, then we are going to get x of k, and this is in frequency domain. Okay, as we are taking Fourier transform on discrete signal, so we are calling it as discrete Fourier transform, and we are writing capital only DFT. So DFT stands for, it is not digital, it is discrete. Remember, it is discrete Fourier transform. So Fourier transform is a process for converting the signal from time domain to frequency domain. That is a signal from time domain to frequency signal. Okay, so what we are doing here, we are performing frequency analysis signal. So that is x of n, discrete time signal x of n. Okay, so as natural occurred signal is an analog signal, we all know that it is an analog signal, it is not a digital signal. So what we do, we convert analog signal to the digital signal. Under that we do sampling. First we do sampling. Once we do sampling, so the resultant signal is your discrete signal, and that one we are writing as x of n. On this x of n, what we are doing, we are taking Fourier transform, and that one we are writing as x of omega or x of k, that is DFT. So this DFT is a powerful tool. It's a powerful for frequency analysis on your discrete signal. Okay, so what we are doing here, we are establishing a relation between a sampled Fourier signal and DFT. So let us consider a signal, periodic signal x of n. Now for this x of n, we will write a Fourier, so now for this we will take a Fourier transform. So if I take a Fourier transform for x of n, then equation becomes x of e j omega. So this could be also written as x of omega. So this is equal to summation n is equal to minus infinity to plus infinity. What is the input? Input is your x of n. On this we are taking Fourier transform. So x of n into e to the power of minus j omega n. Okay, so this one you please take down as equation 1. Okay, now this signal, if you see, so this signal is a periodic in nature. This signal is a periodic in nature, okay, with period of 2 pi. So we will take it omega range, we can take it as 0 to, it is greater than or equal to 0 and less than 2 omega. Okay, so we'll take the range between this. Hence the sampling, if you take a sampled signal here, okay, so if you say this is your sampled signal, this is your analog signals where we have taken these samples. Okay, now these samples are taken at an instance of time, okay, and with the equidistance. So this distance we are representing as del of omega. Okay, and as we are taking for the range of 0 to 2 pi, so this becomes 2 pi by n, and we are taking how many samples? N samples we are taking, and of equal distance. So it is omega will be equal to 2 pi by n. Okay, so we will take, let us hence the spacing between successive sample will be how much? 2 pi by n. So this is equal to omega. So what we will do, we will substitute this omega is equal to 2 pi in equation 1. So this becomes x of 2 pi k divided by n is equal to summation n is equal to minus infinity to infinity x of n e to the power of minus j 2 pi by n kn. Okay, so here we have defined the range of n. Okay, so now we will define the range of k. So this will be equal to 0, 1, dash 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 n minus 1. Okay, so now what we will do, we will try to expand this equation. We'll give the name for this equation. So this equation we will take it as equation 2. Okay, so now we'll try to expand this equation over the range from minus infinity to plus infinity. Okay, so if you see this here, this is your axis. So okay, so this is your 0, minus infinity to plus infinity. We all know that these values are positive values and these values are negative values. Somewhere it will be 1 here, 2 dash dash dash. So this will be n minus 1 and here we can take it as n. Okay, so this is n minus 1. Okay, so this is your minus 1. Somewhere here you will have minus n. Okay, so now if I start from 0, then my last point should be n minus 1 if I take only positive values. Okay, but if I start from 1, then I should take it till n. Okay, so total values should be n only. Total values, how much it should be? It should be n only. So if I starts from 0, if I starts from 0, then my range should be 0 to n minus 1. But if I starts from 1, then my range should be equal to n. That means total number should be n only. Okay, so what we will do, we will try to expand this. We'll write here summation 2 pi by n k is equal to so here we'll try to expand here. First we will substitute n is equal to 0. So plus summation n is equal to 0 n minus 1. See, I told you, as if I starts from 0, then I'm going to end up with n minus 1 because I have started from 0. Okay, so x of n e to the power of minus j 2 pi by n kn. Okay, plus now what will I do? I will substitute. See, I have taken from 0 to n. So next is what I'm going to take it from this capital N. So next range. So this one summation n is equal to, otherwise I can tell like this also. Instead of 0, I'm going to substitute in this equation small n is equal to capital N. So capital, what is capital N? Capital N is your samples. So number of samples you are taking. So capital N defines your number of samples you are taking, and this will defines the range. That is in discrete, what is it, in discrete signal, in what is the discrete signal. So this x-axis is taken as n. Okay, so this n is this one and the capital N is the number of samples. Okay, so n is equal to, if I add n here and if I am going to add here n, so this becomes n plus n, 2n minus n. So x of n e to the power of minus j 2 pi by n kn. Okay, so plus you can take many ranges like this after this. Okay, so I'll take it as write down as dash dash dash. So before this, see, before this is what I'm going to take. So this n I'm going to replace by this 0, I'm going to be replaced by minus n. So if I'm going to replace by minus n, so this becomes so it is minus n to minus 1. So this plus n and minus n will get cancelled here. So this becomes x of n e to the power of minus j 2 pi by n kn. So plus many ranges are here also, so we are not writing, we are taking only two value dash dash dash. Okay, this above equation we will represent it as individual summation. So individual summation could be represented as, so what we will write, we will try to compact this equation and try to write it in one equation. So this becomes summation L is equal to minus infinity to plus infinity. So summation n is equal to L. So this variable L and capital N. So this here it becomes L n plus n minus 1. Okay, so for this only, for this range only, what we have done, we have added ln. So down also I have added ln and here also I have added ln. So this becomes x of n e to the power of minus j 2 pi by n kn. Okay, so in this equation what will I do? I will try to change the value of n, that is n minus ln. Okay, so if I take it like this, so this becomes ln if I take like this here, so this becomes n minus n. So n minus n is what? 0. So this will be value of ln. So this value I'm going to represent in above equation, in this equation. So the equation becomes, and I'm going to interchange this summation. Okay, so if I interchange this summation, so this becomes n is equal to 0. if I'm going to apply 0 here also, so this becomes n minus 1, open the bracket. So summation L is equal to minus infinity to plus infinity. See, n what we have taken as n minus ln. Okay, so into e to the power of minus j 2 pi by n k into L minus ln. Correct? Okay, so this is the equation. Now what this equation, what will I do? I'll expand this equation. If I expand this equation, so what will happen? So summation n is equal to 0 to n minus 1. Okay, so we will expand this. So this becomes L is equal to minus infinity to plus infinity. So this one I'm going to write it as it is, n minus ln. Okay, so into e to the power of minus j 2 pi by n kn into e to the power of minus j 2 pi, is it minus j? No, it is minus into minus, so this becomes here plus. Okay, so 2 pi k ln divided by n. So this n and this n will get cancelled. Okay, now this equation, what is this? E to the power of j 2 pi. Okay, so this one I can use here Euler's identity. If I use Euler's identity, so this will be equal to cos 2 pi. So as it is plus here, so I'm going to use plus j sine 2 pi. Okay, so what is cos 2 pi? Cos 2 pi is 1 plus what is j sine 2 pi is 0. So what I'm going to get? I'm going to get this as 1. Okay, so k and l is what? Integers. K and l. So this k and l is what? These are the integers. So this one I can rewrite it as n is equal to 0 to n minus 1. Okay, open the bracket. Summation L is equal to minus infinity to plus infinity x of n minus ln. So into e to the power of minus j 2 pi by n. Okay, kn. So this one I'm going to replace it as 1 to the power of kl. Again, see, 1 to the power of what will be? It will be kl. So as both are integer, any value of kl, it's going to give me 1 only. So this whole term I'm going to replace it as 1. So this will be the equation. This one I'm taking it as a value, that is, I'm going to represent this whole term as x p of n. So p will tell you it is a periodic. So p represents here periodic. So this equation, the above equation, changes to summation n is equal to 0 to n minus 1. So what is this? This becomes xp of n into e to the power of minus j 2 pi by n kn. Okay, so this one, what is the term here? We were using x of 2 pi by n kn. So what is this equation? Is your DFT equation. So equation 3 is your DFT equation, where xp of n is equal to summation L is equal to minus infinity to plus infinity. Okay, x of n minus ln. Okay, now we'll expand this equation from the range. See, it is minus infinity to plus infinity, so we cannot expand such a large term. So what we will do, we will take it as minus 2 to plus 2. Okay, so we'll start expanding here. So if it is minus 2, so this becomes x of n minus, already minus is here, so one more minus is here, so minus this becomes plus, this becomes plus 2n. Okay, plus next n is equal to minus L is equal, next L is equal to minus 1. So if L is equal to minus 1, so this becomes n plus n. Okay, so plus L is equal to 0 when L is equal to 0. So this becomes x of n. So next if when L is equal to plus 1, so this becomes x of n minus 1, n minus n. Okay, so next plus when L is equal to 2, L is equal to 2, so this is L is equal to 1. this is L is equal to 0, this is L is equal to minus 1, L is equal to minus 2. Okay, so this becomes x of n minus 2n, okay, plus dash dash dash. Okay, now if you see this, I hope everyone knows the equation for periodic. So by seeing this equation, we can tell that xp of n is a periodic repetition of x of n. So what is this? This is periodic repetition of x of n. Okay, hence whatever we are doing, this signal x of n is a periodic signal of period of n samples. Okay, so next we will go for the second part of this derivative, reconstruction of signals. So here what we will do, we already know that xp of n. What is xp of n? We have taken it as a periodic signal. Xp of n we have taken as periodic signal with period n. So it can be expressed in discrete Fourier series. Discrete Fourier series. Now what we are doing, we are expressing this xp of n in discrete Fourier series. It is not transfer. Please remember here, it is not transfer. It is discrete Fourier series. Now if I express this signal in discrete Fourier series, so the equation is xp of n is equal to summation k is equal to 0 to n minus 1. Okay, so a of k e to the power of j 2 pi k n divided by n. Okay, so where see we have defined already, we have defined k here. Now we will define n. So n is equal to 0 1 dash 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 n minus 1. So later in the problems also you can see the range of n and the range of k will be almost same. So k also we are going to take from 0 to n minus 1, and small n also we are going to take from 0 to n, where n is what? N is will be your number of samples. So we have defined here k and we have defined here n. So this equation we will take it as equation number 4. Okay, so now next we will define Fourier coefficient, that is a of k. So Fourier coefficient is defined as a of k. A of k is defined as 1 by n. Okay, summation n is equal to 0 to n minus 1 xp of n into e to the power of minus j 2 pi kn divided by n. Okay, so we have already defined n here. Now we are going to define k. So k will be equal to 0 comma 1 dash 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 n minus 1. So this equation we will take it as equation number 5. Okay, now we will compare equation number 3 and equation number 5. So comparing equation 3 and equation 5. So please compare these two equations. Now you have to compare equation 3 and equation 5. So if you compare, so this whole term, this term and that term will be cancelled. If you see here, this term and it's here. Okay, so this term will be get cancelled. Now comparing equation 3 and 5, we are going to get it as a of k is equal to 1 by n, x of 2 pi by n k. So where k is equal to, we don't have n in this equation, small n, so we will do only define k. So k is equal to 0 comma 1 comma dash dash n minus 1. Okay, now this one what we will do, equation 4 we are going to substitute. Now this one a of k we are going to substitute in equation 4. So if I substitute a of k in equation 4, so then I'm going to get it as xp of n. So now what I'm going to do, I'm substituting a of k in equation 4. So this becomes summation 1 by summation n is equal to 0 to n minus 1. So 1 of n is there, 1 of n I'm going to write it as outside here, this one, 1 of n. Can you see this one? 1 by n, and this becomes x of 2 pi by n kn e to the power of, this term is left, this one, e to the power of plus j 2 pi by n kn. Okay, So n is already defined here. We will define k is equal to 0, 1, dash 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 n minus 1. If you see this, this is the equation for IDFT. Now I'll underline this equation. This equation is the equation for IDFT. So we'll write neatly here this equation. xp of n is equal to 1 by n summation n is equal to 0 to n minus 1 x of 2 pi by n k, open the bracket, so into e to the power of plus j 2n kn kn. Okay, so this is the equation. So we are defining k is equal to 0, 1, dash dash n minus 1. So we can give the number also for this equation, equation 6. So this equation is called as IDFT, that is inverse discrete Fourier transform. Okay. Now if this equation gives you the expression for time domain sequence, that is xp of n from frequency domain samples, that is x of 2 pi by n k. Okay, thus the time domain samples can be reconstructed from frequency domain sampling. Okay, so thank you for watching this video. Please subscribe, share and comment.